So, have you ever wondered why an AI can write a flawless poem one minute and then completely fail to navigate a simple traffic jam the next? Most of us think of AI as this kind of magic box that can solve anything. But if you try to use a chatbot to fly a drone in a hurricane or a self-driving car algorithm to write poetry, the whole thing just implodes. The answer has nothing to do with intelligence. It's because every single problem in the universe has a specific DNA. In the AI world, we call these problem characteristics. And if you don't understand them, your AI is basically doomed before you even write a single line of code. So today we're breaking down these 7 hidden rules that govern every AI problem and how they tell us exactly which tool to use for any situation. Think of it like this. You never, ever use a sledgehammer to fix a delicate watch, right? The problem isn't that the sledgehammer isn't powerful. It's that it is the completely, totally wrong tool for that job. And way too often we treat AI like this one-size-fits-all magic sledgehammer for every problem, when what we really need is a whole set of precision tools. So here is the absolute key takeaway. To really get why an AI succeeds or fails, you have to stop looking at the AI itself and start looking at the DNA of the problem it's trying to solve. In the world of AI engineering, these are the problem characteristics. They are the hidden rules of the game that dictate literally everything. Okay, let's dive right in. We're going to start decoding the first set of rules that really define an AI's universe. You can think of these as the fundamental laws of physics for any AI problem. Getting these down is the first step to understanding everything else. The first rule is all about structure. Is the problem decomposable? This is a fancy way of asking, can we chop a giant, scary problem into smaller, manageable pieces that we can solve one by one without them messing with each other? A complex math equation? That's a perfect example of a decomposable problem. You solve what's in the parentheses, then you do the exponents, and you work your way through. But a game of chess? Absolutely not. Every single move you make, whether it's a tiny pawn or your powerful queen, it instantly changes the entire strategic landscape of the board. All the pieces are totally interconnected. All right, rule number 2. This one is all about the stakes. What happens when the AI messes up? We call this the consequence of error. Is a mistake just a tiny little hiccup, or is it a full-blown game-over situation? And this chart just illustrates that spectrum perfectly. An AI making a little spelling error in an email draft, that's ignorable. No big deal. You just fix it. An AI navigation app that takes a wrong turn, well, that's recoverable. It just recalculates the route. But a self-driving car making a fatal error, that is catastrophic and absolutely irrecoverable. The consequence of error dictates how much certainty an AI needs before it's ever allowed to act. Okay, rule 3 asks, is the world predictable? In a game of Sudoku, the rules are totally fixed, and the grid doesn't just suddenly change on you. But the stock market, it's the very definition of unpredictable. It reacts to news, to rumors, to global events in ways that are just chaotic. And this also brings in our 4th rule. Is it a single agent or a multi-agent world? Sudoku is single agent. It's just you and the puzzle. The stock market is multi-agent, with millions of buyers and sellers all acting at once. Rule 5 is all about timing. Is the world static, or is it dynamic? A crossword puzzle is static. It just sits there, patiently waiting for you to figure out the next word. But a soccer match is incredibly dynamic. The ball, the players, the clock, everything is in constant motion. And that leads directly to Rule 6. Is the problem discrete or continuous? A crossword is discrete. You fill in one box at a time. Soccer is continuous. The action never stops. If an AI hesitates for even a second in a dynamic, continuous world, that opportunity is gone forever. Okay, so now let's move on to our final critical characteristic. This one is all about the information an AI actually has access to. Does it have a kind of God's eye view of its universe, seeing everything all at once? Or is it operating with blinders on, forced to guess about what it can't see? This is rule number 7, and it's the difference between perfect and hidden information. In a game like chess, the AI sees the entire state of the world. Every single piece is visible on the board. But in a game of poker, the most important information, your opponent's cards, is completely hidden. An AI in this kind of world has to reason about probabilities and human psychology, not just logical moves. So why do these 7 rules matter so much? Well, because as they're laid out in foundational AI textbooks like Artificial Intelligence: A Modern Approach, they are the diagnostic toolkit for engineers. A static, predictable, single-agent problem that has perfect information might only need a simple search algorithm, but a dynamic, unpredictable, multi-agent problem with tons of hidden information, well, that's when you have to bring out the big guns, the massive neural networks. And this framework isn't just some abstract theory. It's actually the key to understanding the entire next evolution of AI, agents. These aren't just chatbots, these are systems designed to actually act in the real world. Research defines agentic AI as systems that are proactive. See, they don't just sit there and wait for your next prompt. They take a high-level goal, something like, hey, plan my trip to Chicago, and they break it down into sub-goals, decide which tools to use, like a flight booking API, and then execute a whole multi-step plan to get it done. So how do they actually do it? Well, they're basically operating in this constant cognitive loop. First comes perception. They read the state of their world through text, sensors, or APIs. Second is planning. They decompose the goal into smaller steps, just like we talked about with rule number 1. Third is execution. They actually take action using tools. And fourth, and this is the most crucial step, is reflection. They analyze the outcome, critique their own performance, and then adjust the plan. This loop is what allows them to navigate our complex, dynamic world. And look, not all agents are built the same. As this table shows, different agent architectures are designed for different types of problems. For example, some architectures, like BDI, are really good for making decisions that we can easily understand, but they kind of fall apart with high uncertainty. Others, like React, are super fast and efficient for simple tasks, but they can make mistakes choosing the right tool. The key takeaway here is that the architecture has to match the problem's DNA. And here's the catch. As a problem gets more dynamic, more unpredictable, and the consequences become irrecoverable, the number of possible futures the AI has to calculate just explodes exponentially. This is exactly why we haven't solved citywide traffic. The problem is just too chaotic. So instead of trying to calculate everything, AI uses what we call heuristics, basically educated guesses or smart shortcuts that allow it to find the right answer almost all of the time without having to boil the entire ocean. Now, this isn't just some technical puzzle for engineers to solve. Understanding these problem characteristics has massive real-world consequences for safety, for policy, and for how we manage risk as a society. In fact, governments right now are creating official definitions for high-risk AI. This definition of safety impacting AI from a White House memo focuses entirely on the potential for catastrophic failure. In other words, the irrecoverable consequence of error we talked about back in rule number 2. This is our framework playing out at the level of national policy. So what does this all mean for you? Well, it means you now have a brand new toolkit for thinking about artificial intelligence. The next time you see an AI fail spectacularly, resist that urge to just call it stupid. Instead, put on your analyst hat and ask the right questions. Was it a dynamic problem being treated like a static one? Was there hidden information it couldn't see? Was the consequence of making a mistake irrecoverable? You now have the tools to actually decode the failure. And getting this right isn't just some academic exercise. According to Grandview Research, the market for these intelligent AI agents is projected to hit over $50 billion by 2030. The organizations that master matching the right AI to the right problem are going to be the ones that win. So I'll leave you with this. Of all these characteristics we talked about, which one do you think is the ultimate frontier for AI? Is it navigating these crazy, dynamic, unpredictable worlds? Or is it something more subtle, like mastering the hidden information that's buried deep in human emotions and intentions? I've linked the foundational research on these topics down in the description. Let me know what you think in the comments.